Hello everyone, welcome back to Simoscope. In this video, today we have an electric circuit, and that circuit is a complex circuit, and we are going to analyze that AC electric circuit using the Thevenin's theorem and validate the theoretical results using this MATLAB Simulink model. I already have MATLAB Simulink model built, so firstly I'll show you the an electric circuit. Mm, okay. This is an electric circuit, the figure 19.42. Uh, the circuit consists of the AC voltage source Vs, which is 170 volt at the angle of 0 degree, and mm, we have a load of 100 ohms connected to the X and Y branches. So let's say uh, at the left X branches, it consists of 85 ohms of resistance and uh, the inductive reactance of 200 ohms. At the right hand side, the Y branch consists of capacitive reactance of minus J 100 ohms and 50 ohms of resistance. Now what we want to do is we want to find the voltage across the load RL, and we want to calculate the current passing through that load. To do that, the circuit is pretty complex, and therefore we have to first simplify the circuit and make it more easy and simplify so that we can mathematically calculate. To do that, we are going to use the Thevenin's theorem. Thevenin's theorem, and after calculating the Thevenin's theorem, I already have a Thevenin's circuit here, which I will explain to you after explaining the other process. Okay, what is the first thing we have to do? The first thing to find is the Thevenin's voltage, and Thevenin's voltage is VTH, which is found by Vx minus Vy. What is Vx? Vx is a voltage across the X branch, and Vy is a voltage across the Y branch. To do that, we have to remove the load resistor from here and make an open circuit between the X and Y. The open circuit voltage across the X and Y will give you the Thevenin's voltage and Vx minus Vy. I have already calculated the Thevenin's voltage, which is 110 minus J 6.87 volt. The AC phasor, and this is using the AC phasor and the voltage divider rule. Its polar form is given here. Next is the determination of Thevenin's impedance. We have to find the Thevenin's impedance, which is ZTH. To find the Thevenin's impedance, first we find the impedance at X branch and impedance at Y branch. Impedance at X branch is 71.8 plus J 30.5, and similarly here we add up to find the total Thevenin's impedance of ZTH, which is 112 plus J 10.6 ohm. You can see that the circuit has dominance of reactance with the minor inductance reactance components, inductive reactance components. Finally, everything was simplified, and we have a equivalent voltage source with Thevenin's, then equivalent impedance of Z Thevenin's, and by reconnecting the load, we are getting this circuit, this electric circuit. what we have done, we have just simplified this complex model as electric circuit into the more simpler Thevenin circuit. We have Thevenin at the source, then Thevenin impedance, and the load is connected back to the load. So now we can simply calculate the load voltage across X and Y. And how do you find that? Load voltage is found using the voltage divider network rule. VL is equals to Thevenin times RL divided by Thevenin plus RL. And mathematically calculating it, we are getting 51.6 minus J 5.82 volt, which is 51.92 at the angle of minus 6.43 volt. This is in degree and this is in radian. Okay. And the load current calculation, very simple. I is equals to V by R. So VL divided by VRL is simply 0.519 at the angle of minus 6.43. Okay, we are going to now model this simplified model in the Simulink, and I already have the model here. Okay, in this Simulink model, at the first stage, we have our input parameters. These three constant blocks are configured to then input the complex parameters. First one is the Thevenin voltage load. This is a load, and you have a Thevenin impedance, or the total network impedance. So at the stage 2, each of these are given to the complex to magnitude angle block, and this block transform these rectangular variables into the magnitude and phase array. Magnitude and phase. So this is we are processing this rectangular variables. Now at the stage 3, we have a math operators. This operator is doing the ratio. Okay, this is doing VL is equals to V Thevenin times RL divided by Z Thevenin plus RL. That means we are finding the VL. This is also VL magnitude and the phase angle, and this is the rectangular form. By multiplying with Thevenin, then dividing, this is for the angle, and you're getting the phase angle. From here you get the magnitudes. By using the magnitude angle to complex model this block, we are reconstructing the values back to the rectangular form, and our final load voltage is 51.6 minus 5.282 volt. So this is the load voltage, and by mathematically calculating it, we have also got 51.6 J 5.82. 51.6 5.82 J 5.82. Okay. Now using this value, I have a sine wave block, and my magnitude for the sine wave is 51.92, and my phase is 0.1123 radian. My phase is in radian. So by giving it to the sine wave, I am generating the load voltage waveform here. It is a sinusoidal wave, and the maximum load is 51 volt at the angle of minus 0 point something, 1 something. Okay, that's all for today. What we have done is we have an complex electrical circuit. We mathematically simplified it into a Thevenin equivalent circuit, and then we have modeled this in a Simulink model, and we run the model to verify the theoretical values or the theoretical results that we have got. So that's all for today. I'm going to upload this Simulink model in Gumroad. Please go through my link, and please do not forget to like, subscribe, and comment on my videos. Thank you.